From here to the stars, I am your host, Stephen Euin Cobb. Our guest today is Dr. Mark A. Schneegurt. He is professor of biological sciences at Wichita State University. In addition to being a scientist and educator, he is also an entrepreneur and author. His books range from scholarly works on science, religion, and literature to popular books on the singing group The Beatles. He has authored over 80 publications and has made over 200 public presentations of his works. He founded Open Charm LLC in 2013 to support his products and services. Thank you, Doctor, for taking the time for this interview.
Thanks. Glad to be here.
Okay. In 2022, you were a guest speaker at the Galaxy Forum in the Cosmosphere in Hutchinson, Kansas. You spoke about Wichita State University's then upcoming Spring 2023 Interstellar Seminar. If you would tell us about that seminar.
Thanks. Interstellar Seminar is a pioneering course in space sciences. It's a non-technical exploration of interstellar studies. It's meant to introduce students to the interstellar community. We want them to think of themselves as part of a multi-star civilization. And so how do you attract students to that? How do you change their mindsets to realize that that's a possibility, and not just a possibility, but coming? So we created Interstellar Seminar to introduce students to these topics. Each week we have a remarkable speaker come and visit with us, typically remotely. Many of these speakers are some of the top individuals in their field, from technical topics like the science of rockets, the science of stars, and interstellar travel, to topics that cover life support systems and crew selection and all of the aspects of having peopled missions. And then we end with topics in humanities. We talk about language. We talk about how they would interact with each other and how culture would change over time. And finally, we have speakers that are science fiction authors, because they think about these topics in a broader sense. And it's just a wonderful experience for myself and for all of the students that are involved.
Okay, excellent. Sounds great. Man, I wish I could live closer. I could go to it myself.
Well, I'll tell you, it is archived and is being put online from last year. We're doing it again this spring, and it's open to the public.
Okay.
If you go to Wichita Space Initiative on the wichita.edu/space, you can find the URL for the Zoom for that.
Excellent. I'll check it out. Yeah, excellent. I understand you attended the symposium of the IRG this last year in Montreal. If you would talk about your impressions of that.
I did. It was a great experience. I really enjoyed it. It was an opportunity for me to meet many of the people in this area of study, and it was great fun to be able to talk to them in person. The speakers that they get are top-notch. They are amazing individuals, and I was blown away by a number of the talks. It was really educational for me and socially valuable. So it was a great experience. I really enjoyed it.
Okay. One of your areas of research is hyper-saline environments. What are the ranges of hyper-saline environments? That is, how low can salt concentration be for it to still be designated as hyper-saline? And is there a practical upper limit to a brine concentration?
Thanks. There's no international organization telling us how to use words.
Okay.
So these are not absolutely defined, but typically, if you look at life on Earth, is very sensitive to salt concentration. So even if you're growing bacteria in the salt concentration of the ocean, which is 2 to 3% salt, sodium chloride, that's already a high concentration of salt for most organisms. So 99% of organisms will not grow well in that salt level. In my laboratory, we typically start at about 10% sodium chloride and work our way up from there. So saturated sodium chloride is typically around 32% weight to volume. So we can get up pretty high, and we do have microbes, of course, that can grow in those high concentrations. My lab is also interested in salts beyond sodium chloride because Mars is not necessarily a sodium chloride place. A lot of the solar system is rich in sulfate salts, magnesium sulfate, calcium sulfate. And Mars in particular has chlorate and perchlorate salts, which are not really found naturally on Earth at high concentrations. So we study all of those salts at very high concentrations.
Okay, okay. Most people are only familiar with table salt, sodium chloride or maybe Epsom salts. How many salts are there?
Oh, well, there are thousands of different salts, but
Are there really?
the ones that are relevant to us are things like Epsom salts, which is magnesium sulfate, and sodium chloride. But these other salts that you might find on Mars, the chlorates and perchlorates, these are more oxidizing. These are closer to oxidants for rocket fuels.
Really?
We don't
Okay.
really find them on Earth because they're very reactive, but we find pretty good tolerance to them and very good tolerance to Epsom salts and to table salt. Many organisms grow in these at molar concentrations, very high concentrations. So it's remarkable, but they're very specialized organisms. So I wouldn't say they're rare in the environment, but you have to look for them.
Okay. How do hypersaline environments compare to how salty the ocean is? We already mentioned that, but also other familiar bodies of water, the Great Salt Lake or the Dead Sea.
Yeah, the Great Salt Lake is mainly a sodium chloride place, and it's saturated in certain areas. The lake has been divided into two pieces now by a rail bed, and you can see that one half of it gets very red, and the other half doesn't get as red. And the redder half is the one where the salt concentration is higher, because often you have organisms that are like bacteria. But they're called archaea, and they're very different from bacteria. They're their own group. And they are often found along with the bacteria in very high salt concentrations, and they turn color. They're colored organisms. So they'll be red or pink or orange, fun to work with. The Dead Sea is somewhat different. It's really not dried seawater like some of these other places are. It has a different salt composition. So you'll find sodium chloride, but you'll also find a lot of magnesium sulfate and other sulfate salts. You'll find potassium chloride and what we call the more bitter salts. If you take seawater and dry it down, the sodium chloride precipitates out as it dries down, reaches a certain concentration and precipitates out. And it leaves these other salts that we call bitterns. And these are because they taste bitter as opposed to salty. And these were used to preserve mummies and things like that. And there are a few places in the world where we find environments that are not as rich in sodium chloride. And we study some of those environments that are rich in magnesium sulfate, like Basque Lake and Hot Lake, which are Epsom salt environments.
Okay. You've also measured tolerance of Earth's microbes to other Mars salts. What experiments did you do as far as that goes? You mentioned some of the Mars salts, but I'd like to find out what experiments you've actually done with Earth microbes in those environments.
Yeah, we've been working on them for quite a long time. We started at the Great Salt Plains of Oklahoma, which is a sodium chloride place. And then I said, what other salt can we purchase for $1 a pound? something inexpensive,
Yeah.
because we buy 50 pounds at a time. And
Mhm.
so we started working in Epsom salts, and we were the only group really working in that salt at the time. And it turns out that NASA was really interested in that because Mars has a lot of Epsom salts. And it turns out some of these other worlds do too, perhaps. So we started working at Basque Lake and Hot Lake in the Pacific Northwest. And initially, we isolated microbes that were very tolerant to these salts. And we built up a collection of several hundred microbes. We identified who they are based on their genetics. And we characterize their abilities, their biochemical abilities, and what they can do, what they eat, and what salts they're tolerant to. And then we started to use them in other systems. So we generate Mars analog systems, and usually it's just one or two characteristics at a time. So we might take them down to low temperature and high salt at the eutectic point. We might put them under high physical pressure, like you'd find in the ocean of Europa. We've done a number of things to test their abilities. We currently work in systems where we dry the organisms and then re-wet the salts with humidity alone, deliquescence. We work in soil analogs, synthetic soils that we make in the laboratory, and we work in salt crystals and layered ice systems. So once we find the organisms and have characterized them, we then can kind of put them through their paces and use them for a number of different analog systems.
Okay, okay. You mentioned dry salts on Mars may absorb humidity from the atmosphere and form dense brines. If you would talk about that a little bit.
Yeah, this is a process known as deliquescence. It's a
Mhm.
big word, but you are familiar with this
Oh,
because
yeah.
you know that folks that have uh, dark sugar will stick a piece of bread in there to keep their sugar from getting caked up from brown sugar.
Mhm.
They'll keep it from getting caked up because the bread absorbs moisture better than the brown sugar does. So the brown sugar absorbs moisture from the atmosphere and
Mhm.
deliquesces to some extent.
Mhm.
It doesn't make it all the way to liquid typically, but salts will. And sodium chloride will do this, Epsom salts will do this. And so we look at organisms that start out in a salty brine, we dry that down. They get trapped in the salt crystals, between the salt crystals. And then when they get wet again through this deliquescence process, they start to grow again. And
Mhm.
this was the first demonstration of growth in a deliquescent liquid.
Mhm.
We continue to do that work, and now we're doing it kind of in soils, and we're kind of bringing the temperature down. And we're doing it with other organisms that are part of our current grant program through NASA, looking at organisms that were isolated from spacecraft assembly facilities.
Mhm.
So we're not only taking them from these natural environments, but we're also taking organisms that are the most likely to be hitchhikers on spacecraft to other worlds.
Mhm. Okay, okay. Um, I understand, and this is not one of my questions that I've written down. I understand that Mars research has indicated that Mars probably had liquid water on the surface ages ago. Is this accurate? Are you familiar with this?
Yeah, this is what we think, and we have a lot of evidence for this.
Mhm.
The Mars rovers, the last four rovers, have all found evidence of a history of water on Mars. How long was it wet? Where was it wet? How wet was it? Those are questions that we're still answering, but the consensus today seems to be that Mars was wet for a long time, and there was a lot of water, shallow oceans, perhaps, large lakes at the very least. So
Mhm.
the Perseverance rover landed in the bed of what we believe was a lake and is now driven up through the kind of floodgates where the river flooded in. There's clear deltas like you'd find down in New Orleans and Louisiana, but these are dry, and we're finding rocks that have hydrated minerals, so there's water trapped in the rocks. Plus, we're finding rocks that clearly were altered by water. So when you have a rock that came out of a volcano, a basaltic rock, and you soak it in water for a long time, certain salts and minerals will wash out of the rock and leave other minerals that have been altered. When you find those are pretty good evidence that there was water there, and those salts will then form veins in the crevices in the rock, and we see those things too with Epsom salts, and that's our interest.
Okay, okay. Some people would maybe not be too impressed if Mars turns out to have microbes living in it, surviving from this ancient ocean, like extremophiles living in salt, beds or something. But it would be major. It would be major discovery if there was indigenous life on Mars. Is that your hope that there turns out to be something like that?
Well, the microbes would be indigenous life. They would be native indigenous life. It would show that life existed and continues to exist. So you can talk about past life and you can talk about present life. So the conditions on Mars today at the surface are not very hospitable for life as we know it. Um, in the subsurface, in caves, in other areas, we're not sure. It could be warmer down there, and there could be a lot more water and a lot more going on than we might imagine. Um, but the life previous, before this drying period, could have been more complex. Is it walking, talking humans? Probably not. But organisms that are more complex than single cells, perhaps, we might find evidence of those in these rock samples that we're going to bring back to Earth. So we might find fossilized microbes, but not single-celled bacteria, perhaps things that are a little bit more complex. We're not really sure what we'll find in these sediments that have been preserved for so long. On Earth, we find all kinds of fossils. On Mars, personally, I'm not convinced that we'll see that, but it's certainly in the realm of possibilities.
Mm-hmm. Yeah, the idea of having a completely separate system of evolution on a different world excites me. Just having evidence of that.
Yeah, it is exciting, but there's two ways to look at it. One is that there were separate origins, and there were really two origins of life, and that says something very important. If we find two origins in our small system, that says when we look at other stars, there's so many of them. You have to imagine that there'd be life on other worlds.
Mm-hmm.
If we find life on Mars, it's very similar to life on Earth. And we can define what similar means. Certainly if it has DNA.
Yeah, chemically similar.
Which is an unusual molecule to choose as your information molecule.
Mm-hmm.
If we find things that are that similar, then we're looking at probably a common origin.
Yeah.
And something like panspermia, where life either originated on Mars and came to Earth, or life originated on Earth and went to Mars in a meteorite.
Mm-hmm. Yeah, I've interviewed someone that was a specialist in meteorites, and they were talking about collecting meteorites in Antarctica because they're on the surface and they're easy to spot. And there's a percentage of them are from Mars. They verified they're from Mars. And so theoretically, we could also be taking some to there, although it'd be less because Earth's gravity is so much stronger than Mars. But still, there would be an exchange of material, and maybe a microbe or two traveled, between the worlds.
Yeah, there certainly are exchanges of materials from all the worlds. We have pieces of all of these worlds on our planet now, and we've spread our pieces around, I'm sure. And there's been a number of studies that have looked at how microbes might survive trapped in a meteorite, in a crevice, and how deep they would have to be, how they would handle impacts, and how they would handle the heating and those types of things. And I think the general idea is that seems relatively survivable for microbes to make the trip from Mars to here.
Yeah, even if 99,
the biggest concern is radiation.
Yeah, even if 99% of the microbes on a rock die and one survives, it might be enough. Yeah.
Yeah.
Let's see. And I have some questions about that, but I'm going to move on with this one here. You have also studied microbiology of hyper-saline environments relative to the ocean worlds, the moon of Saturn, Enceladus, and Jupiter's moon Europa. The Cassini probe was able to sample the plumes outgassing from Enceladus and found water vapor, methane, organic molecules, and salts. If you would talk about your experiments in this area, if you would.
Yeah, this extends our work with these salty microbes that we've isolated. So some of the conditions we look at would be suitable for both Mars and the ocean worlds. High magnesium sulfate, Epsom salt concentrations in the water may be something that we find on both of these worlds, both of these types of worlds. Specific to the ocean world might be other salts like ammonia, ammonia salts, or ammonia itself, or ammonium salts. These really lower the freezing point of water. We put salt on our roads so that the water freezes at a lower temperature and stays liquid longer. On these other worlds, we can get liquid water, which is required for life as we know it. And so liquid water is precious, and NASA's been following the water for a long time. One way to get liquid water on a really cold world is to make it very salty. So if you have salty water, it's going to stay liquid at a much lower temperature. And this is what we find in the icy worlds, in the icy ocean worlds. And ammonia salts, or ammonia itself, will lower that freezing point of water to minus 100 degrees Celsius. So the water would still be liquid at minus 100 degrees. Epsom salts only get you down to about -4. Table salt gets you down to about -23. So, and the perchlorate salts can bring you down to -70, and we find these on Mars. This is why we're interested. But if you look at the ocean of Pluto, it's probably somewhere near this -100 degrees. And so we say it might have these ammonia salts. There's other ways to do it, but ammonia is pretty complex. So we look at ammonia tolerance in our organisms and try to find and ammonia is usually a disinfectant, so you don't expect to find a lot of tolerance. But our organisms do pretty well in them. They're pretty tough. The other aspect of our work that's specific to the ocean world is examining tolerance to high physical pressure, hydrostatic pressure. So we have what we call the pipe bomb. It's just a pipe, and we can put microbes in it, and we can pump that up to 10,000 psi. That's about halfway down the ocean of Europa. So 500-600 atmospheres pressure. And the microbes do quite well. It doesn't seem to bother them. We haven't determined whether they're growing or not, but they're certainly surviving under these conditions pretty readily.
Okay. You mentioned the oceans of Pluto. Have we verified that Pluto has oceans?
I believe that Pluto has oceans under its ice shell.
Okay. But it's not been absolutely proven, basically.
Do we prove anything in science? I mean, I guess until we go there and drill into it, but it's my understanding that from the New Horizons mission, that there's pretty good evidence that there are oceans on that Pluto and Charon are ocean worlds, as are many of these larger moons.
I wouldn't doubt it myself, but I was just asking if there was, overwhelming evidence.
Yeah, I really think that they are ocean worlds, and there's a lot of ocean worlds. You can go further out, and probably worlds like Sedna are ocean worlds, and I think these are the types of worlds that we're going to be able to identify on as exoplanets around other stars. I think that we'll find that they're ocean worlds. We're already starting to get information that's leading us to believe that they're ocean worlds.
Okay. I don't remember the diameter of Enceladus right now, but I remember being surprised that it clearly had an ocean world because it had plumes coming out of it. And its diameter seemed very small. to have an ocean.
It is pretty small to be an ocean world. If I'm remembering correctly, it's something like 285 kilometers.
Yeah.
But it's don't hold me to it.
Okay.
It's a small world to have an ocean, and so the current thinking is that perhaps it doesn't have a global ocean.
Hmm.
Perhaps it just has pockets of brine in an icy matrix, and this
Uh,
may be the source of the plumes on Europa as well. It may not
mhm,
be ocean water
mhm,
shooting through the layer of ice straight from the ocean. There may be pockets of water that get trapped in the ices. And then
mhm,
as these separate into heavier brines and pure water ice, it builds up physical pressure. And that is what shoots it out through the crust. We're still trying to figure out how this works, and that's why we're sending Europa Clipper there to help figure this out. But Enceladus or a body like Ceres in the
mhm,
asteroid belt may have just pockets of brine
mhm,
rather than a global ocean.
mhm. Trying to jump ahead and find my question. Yeah. No, I don't see it. Let me go with these. Um, how important is it that we do not contaminate Mars with living things from Earth?
Well, as a scientist, I think it's very important that
Yeah.
we get the opportunity to look at the world
Mhm,
in a somewhat pristine manner. Um, we work pretty hard in planetary protection to get those spacecraft clean. But we know that we can't absolutely sterilize them. There's only been a few things that we've sent to Mars that have been clean to the utmost that we possibly can. So we know that there are some hitchhikers. We want to understand who they are.
mhm,
We want to understand if they would have any chance of surviving and proliferating in those environments. But certainly getting a clean look at these environments on Mars and Europa and other places is really critical to our confidence in claiming that we found life in another world. So if the life that we find is very different than Earth life, then okay, it's easy to say that it's native to that place. If it has a lot of resemblance to Earth life, it gets more difficult to make those same claims. And we're going to try and at least keep areas of it as clean as we possibly can. We tend to try to stay away from areas that that are in special regions, that are habitable zones. So these would be places where we expect to find water. But we realize that with crewed missions, we're going to have to be in areas where there is water because that's how we're going to make fuel. That's
mhm,
how we're going to supply the astronauts with water. So some of these areas where we think there could be more chances of habitability are going to get visited. And humans are messy. So we can't, once we send humans there, humans are messy. And, there's a lot of philosophical discussions that we can have about intrinsic and extrinsic value. And should we wait? Because there is only one Mars and it's relatively pristine now. We could send people anytime. Does it have to be now? So there's a lot of arguments in there. I work with somebody at WSU who writes books about this and the philosophy of space,
mhm.
and it's a very, very deep topic. That said, it looks like we're going forward. So we can talk philosophically, but the practical,
Mhm.
practically, we're headed that direction pretty soon.
Okay. Is your opinion on the topic clear and simple, or are you conflicted?
It is a very difficult topic. I mean, I think that some people make some really important points about making our civilization multiplanetary to preserve what we have. And again, there's philosophical discussions about what preserving what we have means. What are we actually preserving? And
Yeah.
who do we send? Who gets to go? There were some excellent talks about this at the IRG meeting this summer.
Mhm.
And how do you choose and who gets to go and what are we preserving? It's really, it's a deep area. As a scientist and somebody who got involved in science because of the space program, I'm excited either way. Mars is a pretty big world. I think there's room for both.
Okay. Let's see. Let me step outside my science questions for a moment. You have authored a series of Beatle travel guides. I'm guessing you're a big fan of the Beatles. If you would describe these books.
Yeah, these are just for fun.
Mhm.
I am very interested in the Beatles and have been since I was a child. And my wife and I had taken a trip to Hamburg, Germany, quite a few years ago. And when the web was very young in its first year, I put up a website about that trip and the sites that you could find at in Hamburg, Germany, that related to the Beatles, where they
Mhm.
played, where they slept, where they ate, where they went to school, all of these different kinds of
That's where
things.
their career really started off, right?
Yeah, I mean, it started in Liverpool, but they really hit it kind of bigger time in
Mhm.
Hamburg,
Okay.
and became the Beatles there. They all those years of playing for 10 hours a day and just and all of that, the way that they lived really made them into the Beatles, and such excellent musicians, so accomplished. And so I had this website for a long time, and I learned how to write iPhone apps and started to make iPhone apps of my Beatles site. And I said, well, I have the Hamburg one. Let's do someplace else. So I did France. And then I'm like, let's do a place in the United States. So I did Illinois because there's really amazing George Harrison history in Illinois because his sister lived there.
Mhm.
And it's the first place that a Beatle ever played in the United States live on stage in 1963.
Mhm.
But so I started to make these apps, and then Apple called me on the phone and said, "You're really not a programmer, are you?" And I'm like, "Well, like, they're like, you're really not a programmer." And I'm like, "No, I'm not." And they said, "These would make great books. So why don't you publish them?" So I published them, and I have one from Michigan and Indiana and Illinois, and working on Minnesota and Wisconsin someday.
Okay, okay. I was particularly interested in the Illinois book because I grew up in Chicago. So, yeah. But
Yeah.
I'm now up there visiting my brother. Maybe later this year, I might check out some of the sites.
Oh yeah, it's pretty cool.
Yeah, yeah. Let's see. You are the owner of Open Charm LLC. It's described as scientific consulting in applied and environmental biology for research, industry, media, and legal. Technical reviewing, textbook authorship, public speaking, creating books, ebooks, apps, and related items. What are some of the projects that you've worked on, and what are you open to in the future?
Uh, Over the years, I've done consulting for a number of different companies and government agencies, generally in microbiology. I have a long history with cyanobacteria, blue-green algae, and they pollute waters and produce toxins. So people want to talk about that. I've worked in applied environmental microbiology and wastewater treatment and bioremediation over the years. And so I've done some consulting in those areas. Um, so I have the LLC just to run that consulting operation, and I also publish my books under that as well. So it's a I don't even know if it's a micro company. It's a nano company that I run these things through.
Okay, okay. I've got five questions on life in the universe, and I'm going to ask you one at a time. The first one is what you've already touched on a little bit. Do you believe there's life, even if only bacterial life, somewhere in the universe other than Earth?
I believe that there is.
Hmm.
I can't imagine with the number of worlds that are in habitable zones. And habitable zones, you have to really expand because by our standard definition, Europa is not in a habitable zone. It's too
Hmm.
cold out there, but it is habitable, it
Hmm.
seems. So I believe with the trillions of stars or far more than that. I don't think that living systems are that complicated to arise. The molecules of life are everywhere. We find them everywhere we look. We find them on interstellar dust grains. We find complex hydrocarbons and porphyrins and all of the things that you need to build cells. So it just seems to me that given liquid water, these reactions would occur over time. And so I personally think that the universe is teeming with life.
Yeah. Plus, if you have a planet where there's liquid water and you get as just one microbe, then their place is covered with them because they self-replicate.
Kind of, kind of. It's not
Yeah.
quite as simple as that because
Okay.
to really get an ecology, to really get something that's sustainable, you need all different kinds of microbes that do different
Ah,
tasks.
okay.
The nitrogen cycle, the carbon cycle, all of these things, you're not going
Hmm.
to find that, at least not on Earth, you're not going to find that in one microbe.
Oh,
So
okay.
to make an ecology that's going to last, you need
Hmm.
a community of microbes all traveling together.
Well, in the early Earth, uh, my impression was that one microbe came into existence, and it was more of a general purpose microbe, and it was able to thrive and reproduce and then differentiate into others over time.
Well, I guess if you start off with an environment that is rich in organics and rich in the foodstuffs of life,
Hmm.
that one could land in there and start to do its business and then differentiate,
Hmm.
because eventually you'll use up those resources. So
Oh,
it would
yeah.
have to have the ability to adapt to those environments. But typically, we think of life having that adaptation. So that's a good point. You could get
Hmm.
over time adaptation to these environments.
Okay. And as long as I'm trying to make good points, I'll hit one more. The habitable zone, um, tidal, uh, deforming, producing heat, like in Europa, that the habitable zone, they usually define it as, being this distance from a star. Then so you're being warmed by the star, but the tidal heating can also make a subsurface ocean, uh, into the habitable temperature, even though you're way far from the star. It's a
Yeah,
possibility. Yeah.
absolutely. No, that's what's happening in
Mhm.
our solar system.
Mhm.
That and radioactive materials that are left in the core and the rocky core.
Right, right.
Those are the kinds of things
Mhm.
that keep the oceans of Europa and these other worlds liquid.
Mm.
They're
Mhm.
salty, perhaps, which can help, but um, they're certainly a lot warmer on the inside and have a lot of liquid water. Europa has more liquid water than the Earth.
Mhm.
And it's a much smaller world. So I expect to find these around a lot of exoplanets, and I expect to find them as exoplanets around stars as well.
Mm.
These water worlds that have frozen surfaces, but then oceans below, and the floor of these oceans uh, are expected to have outgassing from volcanic activity underneath
Mm.
the surface. So these hot thermal vents that release a lot of minerals that can act as food, that have energy in them that organisms can eat.
Kind of
Uh,
like in the bottom of the Earth's oceans.
exactly like the bottom in the Earth's ocean. And
Huh.
that's what we saw when we went through the plumes of Enceladus was evidence that there was silica particles of certain sizes. And this was indicating to us that there might be black smokers down at the bottom of that ocean.
Wow.
So now
Okay.
you have energy, you have oxidants at the surface to burn them with, and that's more of a challenge is how do you get the oxidants down into the ocean? But if these oceans, if you have something like Europa and it gets hit by a large body, it's going to crack through that ice and it's
Mhm.
going to start to break up and it's going to mix and it's
Mhm.
going to bring oxidants down into the ocean. So
Mhm.
we can see that it's broken up. So we know that this is happening.
Mhm. Okay. Okay. Do you believe there is intelligent life somewhere in the universe other than Earth?
This one's a little harder. This
Yeah.
one I don't really know. I think it's more difficult to get from a single cell up to intelligent life. I know the Drake equation, and it's really hard to fill in the values for how many intelligent civilizations there may be in the universe. But again, it's a very big place, and it's a very long time period.
Mhm.
And I always tell my classes that we think of humans as the most advanced life form on Earth, but we can't even make our own amino acids. We have to eat them; they're required.
Mhm.
We have to run around and catch our food. Plants have an extra organelle. They have can do photosynthesis in their chloroplasts, and they just sit there in the sun and they use minerals and they get their carbon from the air.
Hmm.
And we're running around. So, maybe they don't write poetry, but you could make the argument that they're a very advanced form of life.
Hmm. Yeah, well, that's true. Do you believe there are civilizations elsewhere in the universe?
Is there a civilization on Earth? No, I'm just kidding. Um,
Yeah.
I mean, it's certainly a possibility. It's certainly a
Hmm.
possibility that there are. And maybe by looking at these exoworlds, we'll see evidence of that. There are signatures for what a civilized planet would look like, what an industrial planet would look like. There are signatures for what a world with life on it would look like. So chemical signatures in the atmosphere. So if we see those, that's evidence that there might be an industrialized society.
Hmm. Okay. Do you believe that, or do you think we are likely to meet other civilizations?
I mean, over the very long term, if they exist, I think that's possible. I think advances in communications would be needed if we're not going to travel to these places over long periods of time. If you start talking about gravity focusing of communications with gravity lenses and things like that. I mean, there's a lot to learn still about how the universe works.
Hmm.
We don't understand even basic things like dark matter. We don't understand black holes entirely. We don't understand the physics of the universe yet. So perhaps communication over longer distances is easier than we think. And we just have to
Okay.
learn that. And perhaps these civilizations, if they exist, just don't recognize us as an advanced civilization yet and are just not communicating with us and just hiding from us. There could be von Neumann probes all over our solar system, and we don't have the technology to find them yet.
Okay. And my last question about life in the universe. Do you feel we should hide our civilization from civilizations more powerful and possibly more aggressive?
I mean, this is a concern. We talk about this in the Interstellar Seminar course. This is certainly a topic of discussion.
Hmm.
Uh, Reverse planetary protection. How well do we have to protect the planet from intelligent life? You know, one of the things that I think about in this context is what they call the point. That's when our civilization has gotten to the point where our cyber life or our computer systems and our robots are intelligent enough that they have emotions that we have to start perhaps treating them like living organisms,
Giving them rights and stuff?
giving them rights. And
Mhm.
you get to a point where the cyber world could take over and wipe out the biological world.
Mhm.
And perhaps all civilizations reach this point and the biological life is destroyed. And the other worlds just wait for that to happen. And
Yeah.
then they come and say, hey, we're the robot world. I mean, I don't know. This is all science fiction, of course.
Okay, okay. Um, you have been examining the formation of biofilms on advanced materials that can be used as coatings for bone implants and cardiac stents. Talk about that a little bit, if you would.
Uh, if we have anything implanted in the body, is going to be infiltrated by cells. And if there are microbes that come along, microbes from your skin, these get down into the wound and they cause deep wound infections. So if you have a knee implant or a hip implant, these bacteria get on the surface, and then perhaps months later, they have grown enough to cause inflammation. And that inflammation causes the bone to retreat a little bit from the implant, and the
Hmm.
implant starts to get loose, and then it can fail.
Hmm.
So this happens in maybe 5% of implants. And so it causes a lot of suffering. You have to take the implant out. You have to pack the wound with cement and antibiotics, wait for the infection to be knocked down, and then put the implant back in. So we were working on ways to deliver antibiotics or make surfaces that are more antibacterial, so that the bacteria don't stick to these surfaces very well.
Mm-hmm.
And I have friends over in material science, and they make surfaces of magnesium alloys of various kinds. And so we were looking to see how microbes stick to these surfaces. And they have a lot of value outside of implants. If you think about antibacterial surfaces on door handles and things that are commonly touched. You can plate them with nickel, you can plate them with other metals, but we might be able to make surfaces that are super water resistant, super hydrophobic, and bacteria just don't stick to those surfaces.
Okay, okay, cool. Um, you're working on a new class of antibiotics called Liptins, Liptins. Tell me about Liptins.
Yeah, this is a project that we were working on, we're not pursuing right now, but uh, there's a lot of antibiotic resistance in the world. Uh, as we use antibiotics, organisms learn how to eat them.
Hmm.
They learn how to pump them out of their cell. They become
Okay.
resistant to them. And so, antibiotics like penicillin, ampicillin, a lot of the psyllin antibiotics aren't as useful as they used to be. The enzymes that break them down have been spread among microbes. And even if we look at things like cephalosporins, these also were like on the sixth generation cephalosporin because of antibiotic resistance. So we see antibiotic resistance for almost all the antibiotics. And antibiotics, the pipeline for antibiotics is relatively empty, or has been relatively empty for some time. We thought we solved the problem. We have all these antibiotics. We thought we solved the problem. And then we get the rise of antibiotic resistance. And a lot of the big companies have gotten out of antibiotics because they're not as profitable as drugs that you take every day, in part. So there's kind of been not as many new types of antibiotics. We've looked at a lot of soils already. There's not as many places to hunt. And so a chemist at Wichita State University, Dennis Burns, had a new chemistry that he had developed. And this new chemistry targeted a unique molecules on bacteria that human cells don't have. So we could interfere with how those fats, how those membrane lipids work, by attaching this antibiotic to them, and then the cell doesn't do so well, and your body has a better chance of knocking it down and killing it. So we were working on the microbiology side of it. How does this chemical inhibit microbes, and how does it inhibit the microbes that typically get people sick? So that was a project that we ran for a few years and published a paper last year on that.
Okay, okay. Um, one of your earlier studies on feather microbiology led to the discovery of plant pathogens on wild bird feathers, perhaps carrying disease over long distances. These have great potential for use in dermatology and the hide industry. Describe this if you would.
So I had a friend at WSU who was in my department, Chris Rogers, who was a bird guy. He studied avian biology. And we were friends, so we wanted to do things together. And I was looking at some literature on the microbiology of birds, and found that a lot of it was done by avian biologists and not microbiologists. And so I thought there was a lot of opportunity for us to do a study in this area. So we captured some live birds, and we looked at and captured the microbes that were on their feathers. So we grew out whatever was on there and characterized them, identified them. And we found that some of them fall into groups that are plant pathogens, which is important because some of these birds are migrant birds and they go from one area to another, can migrate 1,000 miles and bring a plant pathogen from one place to another and cause disease there. We also found that a number of these microbes produce an enzyme that breaks down keratin. And keratin is a molecule that's part of your hair. Your hair is made of keratin. Your skin has a lot of keratin in it. So we were
Do
looking,
feathers have keratin?
feathers are made of keratin.
Ah,
So
okay.
these bacteria are eating the feathers and degrading them
Ah,
to a certain
I
extent.
see.
And so you could use these enzymes for lots of different things. You could use them to degrade bird feathers into amino acids and use it for animal feed.
Hmm.
Not a lot of money in that. You could use it to dehair hides, which is now done with a pretty strong chemical process.
Oh, I see.
And now you could do it with a biological process.
Hmm.
Uh, and you could do things with skin and nails and perhaps soften nails so treatment can get in more easily, or soften plaques on skin so they can be scraped off rather than cut out. So we've been looking at these enzymes in the bacteria that produce them.
Oh, okay. Wow, that's pretty cool.
They're
Yeah.
kind of fun. These are our fun projects.
Okay. Let me ask about some of the papers that you've written in various publications. In 2016, you wrote a paper that was put in the Transactions of the Kansas Academy of Science. The title was Peer Review in Scientific Publication. It seems to be a bit of a critique of the peer review process. Talk about that. I believe it was a series of articles you mentioned.
Yeah, it was. And this came out of my association with Sigma Xi, the Scientific Research Honor Society. It's I think the second oldest, maybe the oldest scientific society in America.
Hmm.
And it's open to students and anybody involved in research, even folks outside of the hard sciences and into engineering and medicine and social sciences. So I'm involved with that organization for a long time since I was in graduate school, which I won't say how long ago that is.
Okay.
And the society was founded to promote scientific ethics. So that's an important part of their mission. And I'd seen a few talks at one of their meetings that was very interesting to me, and decided to give some talks locally. And I gave them at the Kansas Academy of Sciences meeting. I gave them here on my campus. And um, the editor for the Transactions Kansas Academy of Science came up to me and said, "How'd you like to write articles about this? This is interesting."
Mhm.
So we did a series of articles on the ethics and practice of scientific publication. So it talks about how you handle data, how you choose a journal, how you prepare an article, peer review, which is more on the ethics side, the things that you have to do during copy editing, and what you need to do afterwards, after it's published, and supporting that paper. So there were 7 articles over 7 years that
Hmm.
were part of that series.
Okay. Okay. Um, I've heard, well, I've interviewed hundreds of scientists over the last 20, 25 years. And I've heard, you know, complaints about the peer review process. But if you would bring up some of the positive aspects of it. I mean, it's a real mechanism that has real value. Describe that a little bit, if you would.
I mean, the peer review process is indispensable. I mean, not
Mhm.
just for publications, but for grants. I've been involved in a number of peer-reviewed grant panels, and these are done with the highest ethics you can possibly imagine in terms of keeping the information proprietary, in terms of treating people fairly. And I have to feel that the process for publications, for papers, is similarly done. I know it is by me. I take it very seriously, and I uh, never use it to my advantage, the information that I see in there, and never try to limit somebody's publication so that I can beat them to the punch or something. I honestly, I really just don't think that that happens.
Hmm.
I mean, maybe there are isolated cases perhaps, but I really think that scientists have a lot more integrity than that. Because in science, all you really bring to the table is your integrity. You say that you ran an experiment and you got this data. There's no evidence that you did any of those experiments, but so we all trust each other in that way, and uh, it's really the only way to examine these manuscripts. Who else is going to understand them to know that the science is any good? It has to be peers that look at it. It's time-consuming, difficult process, both for the authors and for the reviewers. It is challenging. We're talking the highest level of science discussions. But I really think it's very well done and indispensable.
Okay. Also, you didn't mention it's unpaid.
It is unpaid, yes. It's paid by other people doing the work. It's a barter system
Yeah,
for our
yeah.
time because somebody's reviewing my papers, my manuscripts, and I'm reviewing their manuscripts.
Hmm.
And not for friends. It might be somebody that I've met, but
Hmm.
of course we don't do any reviewing for friends or anybody at our university and things like that.
Okay. Yeah, yeah. You also wrote a paper which was published in American Scientist, and the title is 20. It was also 2016. The Other Open Access Debate. If you would talk about that.
Yeah, this is about textbooks for college students, and I guess every grade level. Um, I was asked to write a book with OpenStax Publishing, which is a nonprofit out of Rice University. And they publish open educational resources, OER textbooks.
Mhm.
They're trying to cover right now all of the major uh, large enrollment undergraduate classes across many disciplines. And I had written for a number of years for the major publishers, chapters, ghostwriting, a lot of question banks and things like that. And OpenStax asked if I would write a book for allied health microbiology. And so I wrote a book, OpenStax Microbiology, that's been out for a few years now. And that book is free. You can download it as a PDF or in other formats as many times as you want. You don't need a code. You don't need to prove that you're in a class. You can buy a print copy published at cost. So it's about $50 to print the book. Normally you'd be paying $300 or more. And now you can get the book for free. It's 1,300 pages. It's got a full art program. I think it's better than the books that are on the market. It's more complete and has more uniform in the material that it offers. So this is available for students. There's a biology one that I use in my classes. We're trying to get to open access courses, courses that you only pay tuition and you don't pay anything else to take the course. And so this article that I wrote for American Scientist with the editor of OpenStax is about this multi-generational ethical issue. Most of the information that's in a general biology textbook or even a microbiology textbook, most of that information is decades old. And it was paid for in large part by government money. So now we're charging today's students hundreds of dollars to access that information. It seems like we should be giving that information away for free. And so this is why I wrote the book. I won't say I didn't get paid anything, but I got paid less than 10% than what I would have gotten from a major publisher, and I don't get any royalties from it. None of the authors at OpenStax do. In fact, that's why we call it OpenStax Microbiology. The authors are in there, but it's not the names of the authors on the cover. And this book is open access. So you can reprint it, you can cut it up, you can change it, you can use it for whatever you want, including all of the images that are in there. So this is the way of the future. This is the way education is going to be in the future. And OpenStax is leading the way in that new world.
Okay. Okay. Yeah. Let's see. There is an old theory that life on Earth exists only because the Earth has a large moon. The concept is that our large moon produced tides that caused the ocean to grind violently against the land over many millions of years, and this grinding action allowed the ocean to dissolve vast quantities of various chemicals from the rocks, which of course then allowed life to form and evolve in the ocean. Do you agree with this theory or some modified version of it?
Again, you're getting a little out of my area as a biologist and getting into
Uh-huh.
kind of planetary geology.
Okay.
I would not find this compelling on at face value because I look at worlds like Mars that had oceans, and oceans move because of thermal currents and things like that. There's going to be all kinds of movement. There's going to be freezing and release of waters and floods. There's going to be lots of processes that could release minerals into the waters. I think planetary geology comes into this discussion when we talk about the elements that are available in that system. So you probably know that our sun doesn't generate all of the elements that we find on the Earth. It has a nuclear reactor, but it can't make iron.
Mm-hmm.
It only goes up to about carbon in terms of heavy metals. So these had to have come from other stars. And so are these minerals available? Is phosphorus available? Are these other minerals available in sufficient quantities for life to originate? But I mean, there's a lot of work. You can go back to the 1920s and look at Vernadsky's work, the Russian scientist, and the work on the Gaia hypothesis um, that says that planets don't have life on them. Living planets are alive. And
Mm-hmm.
life is part of the planet and it's all together. That you
Mm-hmm.
couldn't have the world that we have with tectonic plates and things like that if it wasn't for life and having it be a living planet. So,
Mm-hmm.
again, this is getting philosophical.
Let me go back to salt. I have a couple more questions on salt. Everybody knows that without salt, a human being will die if you had all your salt removed. If you would describe some of the functions salt plays in the human body, or is this outside of your field? But the
Well,
reason
yeah.
I ask is because my question is, have microbes evolved to make use of within their biology the extra salt in hypersaline environments, or have these evolved only a tolerance for the presence of the extra salt?
The latter. Mainly it's tolerance to this high salt. They can
Oh,
live in it. They
okay.
don't really use it for energy or anything like that, at least that we know of. I mean, there are significant gradients of salt, but if you let all the salt in, you'd be very salty on the inside, and then you'd have to pump it back out to make the
Okay.
gradient again.
Hmm.
So these organisms actually usually load themselves up with something that's not salt, so that the osmotic concentration between each side, the inside and the outside of the cell are the same. They load themselves up with sugar or amino acids and things that
Hmm.
are what we call compatible solutes. They're
Hmm.
compatible with the activities of life. And so they'll have the same kind of high solute concentration, the same kind of concentration, but it won't be salt. There are some archaea that will use potassium, which is a little nicer than sodium.
Hmm.
But so that's one of the ways, one of the main ways that they protect themselves from the salt. Animal cells don't do that for the most part. I mean, there are some cells that are similar to our cells that can live in much higher salt. There are algae that live in the Dead Sea. And so they load themselves up with salts. And they are protozoans. I mean, they're single cell, but they're not bacteria. And there are other organisms that do well in high salt, like brine shrimp, which are pretty advanced organisms. So there are some that do that, but human cells aren't very good at that. Our cells don't know how to do that and protect themselves. But we need salts as electrolytes to get our kidneys to work and be able to flush things out and just to maintain uh, electrochemical conditions across the cell membranes and a number of other uses for salts in the body. Because, as theory has it, we crawled out of the briny ocean. And if you look at the salt composition of humans, it's similar to the ocean.
Mm-hmm. Okay. And my last question, are hypersaline environments here on Earth different from one another? And I mean different in two different ways. Are they different in their proportion of various salts, but also are they different in the life forms that live in them? In other words, have microbes evolved separately to uniquely fit each of these hypersaline environments, or have some of the same microbes colonized multiple hypersaline environments?
That's a good question. It's one of the questions we're interested in answering in our
Okay.
laboratory. Um, there are lots of different types of hypersaline environments in the world. There's sodium chloride dominated places. There are Epsom salt dominated places. There are places that are rich in carbonates, like Soap Lake, and which has a very high pH. So there's all different kinds of things going on. And then there are some metals that don't seem very hospitable, like iron and such, where we find life in even pretty high concentrations, like Rio Tinto.
Mhm.
So many of these organisms, if you're able to live in a hypersaline environment, it seems like you can live in hypersaline environments. So the techniques that you use are similar. For something like iron and some of these more reactive molecules, it's different. But we find that if organisms are tolerant to sodium chloride, they tend to be pretty tolerant to Epsom salts and magnesium sulfate. So in large part, tolerance to any extreme, not just salt, but temperature, ultraviolet light, pH, a lot of it comes down to repairing your DNA. A lot of these things will damage DNA over time, and how well you repair your DNA has something to do with how long you'll be able to survive in these environments. So there are cellular things like this compatible solutes, but there's other more long-term considerations for living in these harsh environments. But we're still trying to understand this. I'll tell you, we did a study not long ago, published in 2022, where we looked at common soil. So we just went out in the backyard and took soil that's not salty, and we said, how many salty microbes are here? And we found that there were microbes there that can live in 20% salt, which is very high.
Wow.
10%, 20% salt. We're doing a study now where we are measuring microbes in the air. There are salty microbes flying all over the place. And they are able to grow in 20% salt. So why are they there? Shouldn't the environment select them out of existence?
Mhm.
Is it salty in little tiny spots that we don't know in an environment that doesn't seem salty? These are the questions we're asking now.
Okay, okay. Well, thank you, doctor. I appreciate you taking the time for the interview. It's great stuff.
Well, thanks. This was fun. I appreciate it.
Okay. That was Dr. Mark A. Schneegurt. This has been From Here to the Stars, a video series created by the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. Join us October 12 to 15, 2025 in Austin, Texas for the Interstellar Research Group's 9th Interstellar Symposium. Learn more at irg.space. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please hit the like button, and you can subscribe to our channel for other such videos. On behalf of all of us here at the Interstellar Research Group, I thank you.